Good evening. Good evening. I'm Paul Kurtz, the Deputy Laboratory Director for Operations here at Argonne, the Chief Operating Officer, if you will, for the lab. It's fantastic to have you all here this evening. We're really privileged to have a community close by that's so interested in the great science we do here at the laboratory, so it's a real treat for us to have you here this evening. And I have to give Angela credit for scheduling this in between World Series games, right? Because I suspect the crowd would not be quite as large tomorrow evening or last evening. So thank you all again for being here. Well, welcome to Argonne Out Loud, to the end of the earth and the beginning of the cosmos. Thank you all for coming out tonight. I'm always pleased to see such interest in the work we are doing at the laboratory. We're grateful for your support and your interest. This year marks Argonne's 70th anniversary. Our lab was created to develop a peaceful nuclear energy program for the nation. Over the last 7 decades, we've done all kinds of different exciting and challenging science and developed several technologies that we're quite proud of. We've got a fantastic team here at the laboratory, and their accomplishments are many. Certainly I could talk about low carbon transportation, water management, resilient infrastructure, and many more topics. But really all along, during the course of our history, Argonne's basic focus has remained the same, and that's to establish a secure nation and provide people with abundant, safe, and sustainable energy and a healthy environment. Fundamental to achieving those goals is an understanding of the world itself and how it works. As our scientists here at Argonne will tell you, the depths of the cosmos can only be matched by the innumerable questions we have about it. Our scientists follow generations before them in pursuing a clear picture of how the universe was formed. Our current understanding of the cosmos is the best so far, but there's still so much more to learn. But just how do researchers study the beginning of the universe? That's what tonight's speaker, Clarence Chang, is here to tell us about this evening. Specifically, Clarence will talk about his work collaborating with other researchers at the South Pole Telescope. This special telescope is equipped with unique Argonne-made sensor technology to measure and characterize thermal radiation signatures generated billions of years ago. Clarence will also tell us stories from his research travels to Antarctica and the South Pole, which I'm sure are going to be fascinating and quite entertaining as well. Clarence is an assistant scientist in Argonne's High Energy Physics Division and an assistant professor at the Cavalli Institute for Cosmological Physics at the University of Chicago. He obtained a PhD in physics from Stanford University and a bachelor's degree in physics and mathematics from the University of Chicago. In 2013, Clarence received a prestigious Early Career Research Program Award from the U.S. Department of Energy. One of the few scientists recognized on an annual basis in the department in that way. Very prestigious, sets him on a very productive course in terms of his research activities. Before I turn things over to Clarence, I want to invite you to watch this brief video, please.
It turns out we've been given a gift by nature, which is that the first 400,000 years glows. It just happens to glow in wavelengths that we can't see. And so we have to build special detectors to go and look for it. So we do that work here at Argonne. We work here in the Material Sciences Division, with the High Energy Physics Division and the Center for Nanoscale Materials to build these detectors from scratch. And it's a very long process, but we get these detectors at the end that are exquisite in their sensitivity. Once they are made here, we tend to do a round of testing around in Chicago and with our colleagues in the United States, and then we ship them to the South Pole, where they get put on the South Pole Telescope. The millimeter waves that we're interested in looking at are heavily absorbed by water, and the South Pole is extremely dry, and that makes it a great place to look for millimeter wave photons left over from the Big Bang. We're basically taking very long exposures and generating an image And after about 4 years, we get a really good quality image. So we analyze the patterns, and from that we infer kind of what the content of the universe must be. The model that best describes what we see actually involves a lot of energy, but energy that's very different from what we currently see around us. So most of the gravitational matter is dark matter, which isn't what we are made out of. And the rest of the energy is even more mysterious. It couples to gravity in a very strange way. And it seems like there might be even more other things. And we're trying to understand that. For free, we get this story about our cosmic history, kind of where things came from, how things came to be. I think it gets at some of the deeper questions that we kind of are always curious about. And I think that in the lecture, I'd like people just to see a little bit of what Argonne does and a little bit of the value that we bring to the entire human experience.
Please welcome Clarence Chang.
Hi. Yeah. Excited there? You're excited here? Yeah. So I want to thank everybody for coming out on a school night, on a work night, to hear a little bit about the science that I happen to have the privilege of being part of here at Argonne. I think this talk might be a little bit different from some of the previous Outlouds in that oftentimes we think of science and how it affects us through technology, right? So science kind of enables new technology, which then trickles down into our lives, whether it's your cell phone, your GPS, batteries that drive cars, stuff like this. And today's is kind of backwards. It's the reverse, okay? We develop technology that drives science. And that science kind of enriches us through, for lack of a better word, through our imagination, through stretching our minds and giving us a new perspective of kind of what our story is like. So there are a few things that I'm hoping tonight you would leave and take with you. One is that science is interesting. It might seem like a weird thing given how many of you guys showed up here, but science is interesting. I also hope to communicate that science is adventurous, right? Typically, that's not what you think of us nerds, but it can be pretty exciting. And science, lastly, is weird, okay? Yeah, that's right. It's going to defy kind of how we typically experience things. So I'm going to talk about a lot of things that kind of challenge how we think in our experience. And it's important, I think, that we have an open mind. But I'm not too worried because other weird things are going on right now, right? Cubs versus Indians, right? So we are ready. We are primed for weirdness, okay? So I'm going to start off where every physicist starts off, with Einstein, who's the equivalent of Mike Ditka for Chicago football, or Arrieta for the Cubs, right? And we're going to talk about something that normally Einstein's associated with this idea E equals mc squared, but we're going to talk about space-time, okay? And kind of consider three scenarios here. So one is kind of what we're used to experiencing, this, what I call normal. So space is normal, light is normal. Basically, nothing interesting happens, right? So I take this laser pointer and I point it, and light goes in a straight line. And if I block it, I block the light, right? The second scenario is that space basically is normal, but gravity now affects light. So just like you throw a football, and the football eventually comes down to the ground, you can imagine a scenario where now I shine that laser pointer, and far enough away, those photons will start to come back to Earth, right? So this is kind of what you could refer to as the corpuscular theory of light, or basically photons act as footballs. Think of it that way. And the third is this new idea that Einstein had presented a long time ago, which is that actually it's a kind of a combination of both. So it's possible for light to bend, but it's not the light that is moving, it is space. So kind of space bends, space moves. What does that mean? So all is good. So what does that mean? So you can consider a scenario here, okay? These are those two scenarios. So there's the one where you can look at a star, and when that star moves behind the sun, because light travels in straight lines, you won't see it anymore. Okay, that is that normal scenario. You can also consider that corpuscular scenario, the light is a football scenario, in which case what happens is when the star moves behind the sun, the gravity of the sun will bend the light, okay? So you can actually look past the sun, you can look around it, all right? Because gravity is kind of bending the light, just like it bends the football. And then this is a graphical representation of what Einstein was thinking, which is it still bends, but now it's not the light that is bending, what's happening is space is bending. Okay, it might seem like semantics, but there are actually some important differences, right? In particular, the theories predict a different amount of deflection. Okay, so if you were to go out and measure this, so what happens is you look at a star, you wait for our sun, to move between you and the star, right? And a few things can happen. One is the sun can just block the star, right? That's the normal scenario where the light travels in a straight line. The other is that it deflects it through gravity or through bending space-time. And what happens is, so in the normal scenario, you'll get no deflection. In the corpuscular scenario, the football scenario, you expect a deflection that traces this line. And in Einstein's theory, you expect something that follows this black line, okay? And in 1919, so 10 years after the Cubs last won, all right, Eddington went and he found this. He measured it, right? And the dots here are his data, a little cherry-picked, but they are there. And they definitely see that there is deflection, and they follow basically Einstein's prediction. Okay, so there's a profound difference here. There's the idea, the corpuscular theory here, which is that somehow gravity kind of sucks on light. And this one's a little bit more exotic. It says that space moves, right? So as I move across this stage, space is moving all around me. It's reacting to my mass, reacting to my presence, just infinitesimally so, okay? This is weird, right? This is weird. But that is what the data seems to show, right? So we can take this one step further, okay? So stay with me here, okay? So now we generalize it. So not just around the sun, not just around planets and stars, but around galaxies and lots of galaxies. Let's apply this to the entire universe, right? And that's when in 1927, this Catholic priest did. He said, okay, so space-time is stretchy, it moves. So what happens when I consider putting the entire universe and ask what happens when I kind of consider all of that, right? And he came to this conclusion that if indeed space-time is moving in this way, that the universe would be expanding. Okay? And what does that mean, right? So I've kind of put together a little cartoon to try to give some sense, some intuition, what we mean when we say expanding, right? So what here, you can consider these black dots to basically be galaxies. So galaxies sprinkled throughout space. Yeah?
A good example of finding a way out, you could break some raisin bread. You break some raisin bread and you see that they keep going farther and farther away. That's how the galaxy is. Oh, and that guy was also one who got the idea of the Big Bang Theory. Thanks to the expanding universe theory guy, he decided to get the Big Bang Theory from that.
That's right. So someone got the cliff notes to my talk. I'm done. Thank you. That's exactly right. Okay? So I'm going to illustrate the raisins, right? So these black raisins are galaxies. And that's exactly right. So you bake it, the universe expands. I changed the color. And they stretched a little bit, okay? And you keep on letting that go, and they stretch a little bit more. And what you can do is you can think, so what does this look like from my perspective, our perspective? So we sit in a galaxy. If you didn't know that, we sit in a galaxy. And that galaxy doesn't change. So you can imagine, suppose we sit on one of these galaxies, what happens, right? So what I've done now is I've taken those three images, I've stacked them on top of each other, and kept that same galaxy in place. So this is me, or you, in our galaxy, and you're looking at all these other galaxies, right? So the expansion causes us to see them as if they are moving. And they're moving in a particular direction. It makes them look like they're moving away, okay? And the ones that are further away seem to be moving faster, okay? And this isn't that the universe is expanding around some special place, right? This is just because that's where we are. I can repeat this entire thing at another galaxy, okay? So somebody's standing on this other galaxy, and once again, the galaxies that are all moving away, the ones that are further move further, right? And you can imagine it again. So this is just that raisin bread, right? It's just everything's getting bigger. Everything's moving away from each other. And so this is a prediction, right? You can kind of make a little plot. So in the case where nothing's moving, right, you would expect that as I look at galaxies that are further and further away, they would neither be moving away nor towards us. They would just all be still. Okay? In the case as with that Belgian priest, Lemaitre, if the universe is expanding, then as you look further and further away, you would see the galaxies as if they were moving further away, moving faster. And there's the opposite scenario where things are contracting, so you look further away, and they look like they are moving towards you. Okay? And so in 1929, another 10 years later, so cosmology is a very profitable endeavor for retirement. Edwin Hubble makes this measurement. He measures the velocity as a function of distance, and indeed he sees what is consistent with expansion, right? So there is some weirdness here. So you'll know Edwin Hubble always walks around with a pipe. And I claim I'm not getting my discovery because I'm not allowed to walk around with a pipe here at Argonne, right? No, right? No. So this expanding thing, that's very weird, okay? That's very weird. And let me explain a little bit of why. Okay, so you can start developing this idea, and that's exactly what Lemaitre did. He said, okay, so the universe is expanding. Suppose it's just been expanding for all time, right? What does that mean? So he said, okay, I can come up with a few conclusions, and I'll step us through this, right? But he had the sense that the universe early on was hot and dense. And that initial condition, he called this primeval atom, right? And Einstein listened to this theory, and he had this quote attributed to him where, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." That's pretty remarkable. Of course, since this used his theory, perhaps it's a little bit, self-congratulatory, so perhaps we shouldn't pay too much attention. Not everybody liked this idea. Most people actually disagreed with it. So Fred Hoyle, favored this idea of what's called the static universe. He's the one who actually coined the name Big Bang. So Lemaitre did not call this Big Bang. In fact, Big Bang is kind of a bit of a misnomer. Okay, but let me break down some of these ideas. Okay. So what I have here is a little illustration of what we mean by expansion and how that works. So you can imagine this as time going forward, okay? And these cubes represent cubes of space. Technically space-time, but just some cube of space-time, okay? You can look, suppose this is a cube, a volume of space today. Then tomorrow that cube would be bigger because of expansion, okay? And expansion was always going on. Then in the past, so yesterday and the day before, that cube would have been smaller. Okay? And so we can start putting stuff in to those cubes, right? So today it's filled with galaxies and stars and stuff like that. Tomorrow it'll still be filled with those galaxies and stars, but space would have expanded and things would have been less dense. Okay? They would be less dense and they will be colder. Okay? So what if we rewind the clock? What if we look into the past, right? Well, in the past, things will start getting more dense and they will be hotter. And things will continue to be hotter and hotter and hotter as you go further and further back in time. Okay, so this is that hot, dense state. So something interesting will have to take place. So as matter gets really dense, as matter gets really hot, it no longer stays as a collection of atoms, right? So as matter gets really, really hot, eventually the electrons and the protons separate and they kind of mix around freely. And that's what we call plasma, okay? And so at some point in time, in the distant history, the universe goes from being a transparent gas, a hot gas, but a transparent one, to a plasma. And the thing about plasma is that it is opaque. Okay? Opaque means you can see it. Okay? So in principle, in this story where things are expanding, you should be able to see the early universe. Okay? And a critical physical concept associated with that is that light takes time to travel. Right? So everything we see is actually in the past. Light has taken some time to travel from me to you, from me to that camera. Right? When we ask our phone, where am I? It takes about 0.06 seconds to get to that satellite, the GPS satellite. When you look at the moon, that's about a second in the past. When you look at the sun, it's about 8 minutes in the past, right? The further and further away that we look, the more and more into history we see, right? And an important prediction of this whole story is that if you look far enough away, you look far enough back in time, you will see something. You will see the universe glowing as that plasma. Okay? And so this is kind of a cartoon of what that would imply, right? We'd be here in the middle, not quite in a galaxy that looks like this, but, and you'd look out, and eventually you wouldn't see much, and then suddenly you'd see a wall of light. That's the primordial plasma. That's what's predicted by this story. Okay? And in 1965, Arno Penzias and Robert Wilson saw that signal. They saw that we are bathed in photons from the 14 billion years ago, from when the universe was just this hot ionized plasma. Okay? This was taken as smoking gun evidence for what now we call the Big Bang. They also got a Nobel Prize for it, though you can't quite tell from their face. Right? This is just plots kind of showing it, so it is quite robust. So you look everywhere. That is one of the consequences, is that you look in any direction, this is what you should see. And indeed, I know this looks like just a dot, and that's really what it looks like. You look in any direction, and all you see is this light. You can measure the spectrum of the light, that is this color, and we can predict what that should look like, right? It should look like that plasma stretched over the course of cosmic history. And that's exactly what we got. In fact, there are error bars here, but they are so small. They're within the data points, the black dot, right? So we have this resounding story. In some sense, it's definitive proof that this rather exotic narrative of our history is what's going on, right? Wow, that's weird, right? So we started with this idea that space kind of moves, right? That I move around and space kind of ripples around me. And then we took that and we said, okay, if you start encompassing the entire universe in that, what happens? And we get that the space expands, right? And then you follow that through. You say, okay, if that's been happening all the time, then what would you get? You'd get this bright source, and you can see it. We can see it, okay? So this is a picture of that orange blot, only now I've cranked up the contrast, right? This is taken by the Planck satellite. This is fairly recent. But you crank up the contrast, and you find that that orange blob is not actually completely uniform. It's splotchy, right? These are images of what the universe looked like 14 billion years ago, or when it was less than 400,000 years old, okay? And an amazing thing is that we can calculate what must go on there, and then we can infer what the content of the universe must be, okay? And you do that, and you get this really weird story, okay? We know that most of the universe is this thing called dark energy. The rest of it is this thing called dark matter, and the stuff that we are made up of is less than 5% of the total energy content of the universe, right? So there's a lot left for us to learn. So within high energy physics, we spend a lot of time studying this, but we know that this is a new era, that our models are incomplete. And this has become a big focus here at Argonne of a lot of our research, okay? So how do we do this? How do we see our origins, okay? So there's an interesting thing here, that just to get a little technical, okay? The peak here is at 2 millimeters, so this is the wavelength of light, okay? Infrared is somewhere out here, and radio is somewhere here. And the reason I bring that up is because there's very little that detects photons in the millimeter wave. Okay, you can go out, you can buy your infrared camera, just go on eBay, and there's the radios in your car. But at millimeter wave, this is not so easy. Okay, there is no commercial source of high sensitivity millimeter wave detectors. So how do we then go about measuring this? And the answer is we make it. And that's what we do here. This is a picture of the Center for Nanoscale Materials, and we've brought together 3 divisions in Argonne into this endeavor: high energy physics, the CNM, and the material sciences division. And this is a picture of what one of those detectors look like. So I don't know if you guys got a chance. This will be out back after the talk. This is one of our first generation detectors, okay? It's very small. And so what I've done here is I've blown it up so that we can see it. This is only about less than 5 millimeters across, and this is where all the action is. So if you blow that up, you see some superconducting material. Perhaps an interesting thing is to compare this. That is a human hair. Okay, so it's really small, hence the nano. So these get put together, two directions to measure the two polarizations, and then assembled into little modules. So this is about the size of a AAA battery. And we made 180 of those batteries, and we put them around the outside of this focal plane. The inside corresponds to another set of detectors, worked with colleagues at the National Institutes for Standards and Technology. And once you've done this, you go to the South Pole, right? So what does that mean? What does that look like? So that's the ends of the Earth, right? So what we do is we start off in Chicago O'Hare, and the first thing they do is they fly you to New Zealand, right? Which at that time looks like this, because it's summer down there, southern hemisphere, right? So you actually fly to the southern part of, to Christchurch, New Zealand, and there you spend a day getting your clothes. And actually, if you looked out, we had these, right? These are those big red jackets. Canada Goose, fashionable as always, right? You also get boots, and you get these funny gloves, right? To have this little thing so you can rub the frost off your goggles. We can play with that a little later. Okay, so once you've got your coat, got your clothes, you didn't get ready to make the trip. So there are no commercial flights. You just have the Air National Guard, and unfortunately, they do not offer a frequent flyer program. If you are fortunate, you get on the C-17, which might look like this with nice palletized seats. Some of us who are lucky get upgraded to the Hercules, where you get seated in first class like this. This here is the lavatory, and this here is the complimentary beverage service. Okay, the C-17 makes the flight to the continent, 4.5 hours. The Herc, it takes 8. So it's a long flight in Economy Plus. And on the way, you see some interesting things. For the most part, it's just empty water, but as you get close to the continent, you start seeing all the ice. And this is pretty amazing, yeah? And eventually, we do a pit stop just off the coast at McMurdo Station. This is the premier, the primary scientific base of the United States on the whole continent. Everything that goes on in Antarctica feeds through McMurdo. This here is Scott's Hut, of historic significance. For us, this is really just the world's longest layover, because we actually don't have anything to do in McMurdo. We just wait. We wait for weather, we wait for the plane. Those don't always work together, so sometimes you wait a long time. But eventually, you go, and you head off to the South Pole. And here's where the Herc is special, because it has these skis, right? So you go to the pole, and you don't want to fall asleep on that flight, because it starts right off with looking at the Antarctic mountains, right? You start flying over all of that. Tell me if you want me to stop. Okay. This is our destination, the South Pole. You can see the runway that we land on, right? After about 3 hours, we eventually arrive. And the first thing that hits you when you jump off the plane is it's cold. You know, that's minus 40. But just to put that in perspective, that's not too bad different from Chicago, all right? It's not too different. Okay. This is what we're there for. All of that scenery is fantastic, but actually we're there to do work. I don't take vacation when I go there. We get paid. We do work. This is the South Pole Telescope. It's a 10-meter telescope. It's big. Yeah, sometimes you have fun. So in the beginning of everything, right? So the whole point was to take that detector and we put it inside this cabin here and we start looking at the sky, right? This was first light for that instrument in 2012. The graduate student was happy because that meant she would graduate, right? And this is a sped up version of what the South Pole Telescope does. So it just kind of sweeps across the sky, taking measurements. Okay, this is 10 times faster. It doesn't actually slew that fast. That would be scary. This here again is your latrine. okay? And this is that data. So you can look on the laptop, and what's happening is that the telescope is sweeping back and forth over a region of hydrogen gas in the galaxy, okay? And each time the telescope crosses that gas, there's a signal in the detector. Boom, 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 right? Boom, boom, boom. Obvious, I'm happy because it means my detectors work, right? This was extremely successful, okay? Now, this is real data. Not all the detectors work. Not everything works. I myself was trying to grow some facial hair. That was less successful. Right. But at least the detectors work. So now there's a really special group of people who we call our heroes. These are the winter rovers. So we go down. Most of us go down in the summer season down there. So that's between November and February here. Okay, in fact, a couple people from our crew back there are getting ready to leave in just a couple weeks. These people here, though, stay the rest of the time, from February back until November. That's when it is dark, right? When we go down, the sun's out. When they're down there, the sun is down. You'll notice some interesting things, okay? Like these guys did 2 years back to back. This guy did 2 years, right? Dana has actually been there 3 times over the winter season, right? And these guys are nuts because they're wearing short sleeves. But they get to see something that is absolutely amazing, okay? These are some images coming from that winter over experience. Very expensive. You forfeit a whole year of your life. Okay. Now, of course, we're not there to look at the aurora australis ourselves. We're actually interested in what SPT sees. So let me go back. So this is that image taken by that satellite. And we can grab a small patch of sky in the southern hemisphere, right? A small patch of sky, and it looks like this. So this is about 30 square degrees as seen by that satellite. Okay, these blobs here, that's the universe 14 billion years ago. Hot and cold spots, right? Now with SPT, you can see it come into, the image becomes a lot sharper. We can see a lot more details. And that's because we have better resolution and because we have more sensitive camera, right? So we can make out finer features within this pattern relative to that satellite. And you can look at that, and what that means is you can see things that we haven't seen before. So this is a little science highlight just coming out of that first year. We made the first detection of a subtle signal in the microwave background, okay? Our competitors even says this detection is a milestone event in using the CMB to probe our universe. So by making better images of the microwave background, of what our universe looks like way back then, we can say things, more detailed things, about what the universe is made out of. In many ways, this is interesting because we're using the entire universe as a laboratory for fundamental physics. All right? So what are the next steps? So now we see these signals. What we want to do is we want to move from detection to precision. We want to measure things very carefully, very precisely. And you do that by new technology, okay? So this is our latest and greatest set of sensors made here at Argonne in the Center for Nanoscale Materials and Material Sciences Division. They are now more complicated. There's a lot more going on, right? The central feature is an antenna made out of superconducting material, okay? We have additional superconducting circuitry, which filters and processes the light that we get, right? And this is that detector. Again, just a little bit bigger than a human hair, just floating alongside the entire structure. This is made as an array, okay? And this is that picture, Wes. And this is what they look like. They're much bigger, okay? Again, you can take a look at this after the talk. And so with the bigger detector, so we want to put 10 of those in the South Pole, you need a bigger camera. So this is a millimeter wave SLR, or yeah, it's not quite DSLR, but it's SLR, okay? All the lenses are in this unit, and the camera is in the back. Inside there, that's where all our detectors go. You can see the 10 slots. 2 of them have been filled. In fact, this just got packed up this morning to get shipped to the South Pole. Okay? It's all a work in progress, right? And what is it that we are looking for? Okay, so let's come back to this timeline. So here we are, the universe is ionized. And kind of we want to know what happened before that. How did that come to be, right? This is where a little bit of imagination comes in. So we have this theory called inflation, okay? And it has some funny things, okay? It solves a couple problems that we have. So there's something called a horizon problem. And this deals with the fact that if I look at the microwave background in this direction, and I look at it in that direction, I measure the exact same temperature, or pretty much the same temperature. And that's really hard because the photons are only now getting halfway, right? So those patches of the universe could never have talked to each other. So why would they be at the same temperature? That's a little odd. That's a little weird. In fact, it's very weird. It's a big problem. There's also this idea of flatness, which deals with the fact that the geometry of our universe is flatter than we naively would have expected. It's extremely flat, and we don't know why that should be. Turns out inflation solves all of these, but it comes with some weird stuff, right? So it does it by accelerating the expansion. So very, very early on, 10 to the minus 36 seconds, the universe just expands exponentially, okay? It starts from being a quantum state and then becomes the entire universe that we see. It's kind of dramatic, but to give you a sense, that's what it predicts, slowed down by like 10 to the 36. Okay, so you start from an infinitesimal dot, boom, you get the universe, right? And this fuzz here was quantum fuzz turned into the universe that we see today. That's extremely weird. Okay? So as with all the weird things that I talked about, hopefully you've gotten kind of the rhythm of my talk. When something's weird, we ask, is there something you can measure? That's how I stay employed. So you can ask, so if inflation did happen, is there one of these predictions, some logical consequence that must be there? And the answer is yes, okay? And it all hinges on this fact that it takes this quantum state and makes the universe out of that, right? So gravity also takes place. And what inflation will do is it'll take the quantum fuzziness of gravity and spray that all over the universe, right? And when that happens, you get gravitational waves, okay? These waves, these gravitational waves, imprint a distinct signature in the polarization pattern of the CMB, okay? It's very faint. It might not be there, because inflation might not be correct. But if you see it, that's a very weird trip to Stockholm. Okay? So that's kind of the Holy Grail, one of the flagship things that we are looking at. So I wanted to conclude with some final thoughts. So this doesn't happen just by myself. Okay? We actually have a small army there. These are the people at Argonne working with us on making the CMB. A bunch of people are here. If your face is in this picture, why don't you stand up? Let everybody see you. I see you, Ralu, Steve. Most of our crew over there. Yeah, let's give them a hand. Right? These are the people involved in making this, which is a lot of hard work. I wanted to recognize that and appreciate that. And we're only a small group. We're just part of the larger collaboration of the South Pole Telescope. At this point in time, I should also thank our sponsors, the people who give us money. We have private donations from Kavli and the Moore Foundation, but we are primarily funded by the government, by the National Science Foundation and the Department of Energy. Okay? I also wanted to thank a bunch of people who helped me put together the pictures and the images you saw. So Wes, James, and Dan, who put together that video at the beginning. And Robert and Alyssa helped me put up a lot of these cartoons. And I also want to thank Angela in particular, who worked really hard to hound me down and catch us before we head off to pole. So yeah, this is the final slide, the summary, right? So we go to the ends of the world, and we look at the dawn of time and back. So back is important. We've got to come back here, right? And I hope I gave a sense that the universe is really exciting, right? There's this story that space-time moves. That's right, right? Space-time moves. You can bend space. You can bend light, right? And then that becomes the raisin bread that's expanding. And you extrapolate that back in time, and you get this infinite universe, this hot, dense state, which we can look at, which we can study, which can tell us all about the energy content of the universe. The universe is really exciting, right? Science is exciting, right? This whole process of kind of these challenges. Oh, is it a static universe? No, it's an expanding universe. These ideas. What are these predictions? What would be the consequence of your theory? And can you measure that? Can you validate that? And then making the stuff, the stuff that's smaller than a human hair, and taking that all the way to Antarctica and measuring the infinite universe. Science is exciting. And Argonne is exciting, right? So with that, right, go Argonne, go SPT, go Cubs. Thanks.
Thank you. Nicely done. Nicely done. Thank you, Clarence. Yeah, thank you very much, Clarence, really for sharing us some insights into your research and fantastic work of your team as well. It's really a treat for us to hear firsthand from such an explorer, from someone who's really at the forefront of science and discovery. So it's really a treat for us. We have time for a few questions, and I'm going to ask people to wait until you have a mic actually in front of you to actually use so everybody can hear the question. I'm going to also say that I'm going to certainly you can go ahead and hand the mic, but I'm going to prefer or give preference to questions from children and younger folks in the audience tonight. So if I call on the children instead of an adult, please forgive me. So please.
Is what you're doing here take away the need for CERN?
It's different. So the question was, does this work take away the need for CERN? So CERN looks at kind of the stuff that you and I are made out of. And basically, I look at the rest. So we're different. So CERN is very important, very much a part of our program, and doing some very interesting work. It's just different. Okay. I think he's got a question here.
We have a mic here.
Okay, sorry, go ahead.
How do you make the detectors itself? What precision tools do you use?
Okay, yeah. So this is not like what's in your garage shop. It's not like a woodworking stuff, okay? It's a lot of chemistry, a lot of plasma etching. It's basically how we make computer chips, okay, for your phone. We use the same processes, only we do it with superconductors, okay? So it's many, many layers. You have to dress up in those white bunny suits. You have to do a lot of work. All right? Okay. Question?
Hi.
Howdy.
My voice sounds a little weird. All right. Okay, so what does quantum mean? Because I heard quantum theory, quantum state. What does quantum mean?
Good.
Mm-hmm.
Even though I already guessed that you got this from quantum theory, first started by Albert Einstein is NER. I think you guys got this from quantum theory, haven't you?
I think that's a question we are still trying to answer.
All right.
Okay.
Maybe a little inspiration from Schrodinger's cat.
If you can find the cat, be happy to pet it. Yeah. So no, I don't think we have a deep understanding of what quantum mechanics is. This is still an active area of research. Quantum mechanics, if you think this was weird, okay, quantum mechanics is really weird.
Yeah, but I had a feeling you would say something with quantum about having some of the same energy and they don't interact with each other. That sounds completely like quantum theory, saying that even if the two things don't interact, they will either do the opposite or the same properties, even if they do not interact with each other. It always gets the same probability and and the same answer.
Yeah, you are correct. So this is something that's known kind of as those quantum states. Yeah, so you can take things and you can separate them, and then you can look at one, and that tells you what the other should look like without light moving between. That is weird. Okay, that is really weird. And there are other people at this lab who do stuff that is like that, and hopefully they will give it out loud.
Yes.
All right.
Question over here.
Okay, I'd like to say thank you for the presentation because I do need to raise my grade in science anyways. So, what my question was why was the telescope going horizontal instead of vertical?
Okay, it's a good question. It's just how we chose to look at the sky. Okay, so we just slew this way, and then after a bit of time, we then step up a little bit, and we slew again, and we step up a bit and slew again. And we build up our images that way. So we build it up one sliver at a time. So you only did that because I only showed you the first part. All right?
All right. How about a question from an adult at this point in time? One back here, please.
All right, so when you're using the SPT telescope to find something that resembles like the plasma, and you get like the hot and cold spots, how do you know that's what you're looking for?
How do we know? It turns out that the microwave background, so if you look at that 2 to 3 millimeters, okay, it is the brightest thing that is there. There's some subtlety. There are some galactic emission, and what happens is we look at it in several different colors. And the microwave background has a certain set of colors, and everything else looks different. Did that answer your question?
Yep.
Yeah. Okay.
Back down here again. Oh.
Okay. I don't know anything about science, and I avoided chemistry at all costs. So I came here for him, and I've sat here smiling. And I don't understand any of this. I don't even know why. I thought that this was going to be about the stars and this was going to be like an Adler planetarium type thing. Very awesome symposium, very interesting, but I still have no idea what we're looking for, what we're going to find. I mean, what's going on here, really? Layman's terms.
Definition for cosmos, Mom.
Yeah. So at its heart, we're trying to answer the question kind of to put pieces in place as to understanding how things came about. Okay, and we can work things back so far to 14 billion years ago.
So you're just trying to substantiate theories?
Yeah, and so what happens is at that point in time, it looks like some new physics has to be important. It looks like actually that we are, in the theory of inflation, we're all connected to some new form of energy. And we want to know, is that really what's going on? And if so, what are the laws of physics that govern that form of energy? Right? So somehow everything started. And that's kind of the question we're looking for.
Wow. That's profound.
Please.
All right, where'd they go?
Okay, now it's working. Do you have some conventional telescope there, and how you avoid interference from the galaxy when you look up? Does it interfere and give you some false reading or something like that?
Mm-hmm. So I don't think we have, well, SPT actually has some conventional telescopes, so I think we took those off, right, Steve? There aren't really optical telescopes there. It turns out that it's not so great for looking out in the optical wavelengths. So that's the answer to your first question. The second question is, how do you tease apart emission from the galaxy? And that is there. It hinged upon the color. Okay, so the microwave background has that very specific color distribution. Everything else looks different. So we measure several different colors, just like red, green, and blue, for lack of a better word. So we measure at 1 millimeter, 2 millimeter, and 3 millimeter wavelengths, okay? And you can reconstruct the color, and the galaxy has a certain color, and the microwave background has another.
Very good.
Okay.
Question over here.
Yeah.
The diagram that you had of the detector,
Sorry, where's
Here I am, sorry.
Okay.
Had the new detector, which part was actually the detector? Yeah, I think you said and what was that other fancy part?
Yeah.
I'm gonna use
So
the
I
slide
think I have
projector.
to
Sorry.
move back
Okay.
and blow this up. So the question is, what part is the actual detector? This is what does the detecting. That's where you measure the energy.
What is the other thing?
This is an antenna. This is an antenna. Yeah. So you pick up the light here, it kind of moves down these lines and winds up at one of these. Okay?
Yes, my name is Mao. I'm from Moraine. I just want to say a big thank you for the lecture. It was really interesting.
You're welcome.
Also, a big thanks to my professor Hoop for bringing me in here.
All right. Thanks for coming.
Thank you.
Okay, yeah, we got questions on this side. Oh, no worries.
Thanks, great lecture. So is it widely accepted now that dark energy and dark matter is, proven? And if it is this detecting dark energy and dark matter as part of your research?
Mm-hmm. So the question is dark energy and dark matter kind of, are those accepted aspects of the model? And that is yes. We need those ingredients in there to explain not just the microwave background, but a whole host of observations that we now have. Now, we still don't actually know what they are. They're kind of outside of the normal, what we typically think normal matter is made out of. So those are trips to Stockholm in and of themselves. So the first question was that, will we have anything to say about that? So with dark matter, not so much. There's certain small classes of models that we could say something about, basically with dark matter annihilating in the early universe. But dark energy, we do. So dark energy deals with kind of contrasting how the universe looked then with how it looks now. So the more we say about what it looks like then, gives us some senses of what dark energy is doing. It turns out it's a little bit more subtle than that. We also actually see things in what I call the late universe. Most people call that the old universe, but it isn't. These black dots are galaxy clusters, smashing, huge collections of galaxies, and we actually see them. And it turns out these care a lot about dark energy, and understanding how the galaxy clusters work is one of the ways we can try to understand dark energy.
One last one.
Mm-hmm.
Do the laws of physics as they apply to our world, you said they don't really apply to dark energy and dark matter. Do we have a sense of what those laws might be at this point?
The laws of physics do apply, but the particles are different. So the constituents of dark energy is not what you and I are made out of. So in some sense, breaking us apart, well, not us, but smashing normal particles together, it's not directly related. You can't build dark energy and dark matter out of our current building blocks. Something new must appear. Okay. I think there's a question from a kid back there. Yeah.
How did you figure out how old the universe is?
That's a good question. That's a good question. So how do I do this, though? So let's go back to this. Okay, that goes too far back. Okay, let's not look at that. So basically, it's that time when the universe was a plasma. We know what temperature that is, okay? And then from then, those photons come to us, and they travel a certain amount of time, okay? And we can measure the temperature of those photons now. And that distance, that stretching, tells you kind of how old the universe has to be. Okay? It's a little hand-wavy, but probably good enough for your homework. Yeah?
Please.
Hi. When you were talking about inflation, you mentioned one of the problems was flatness. Can you please expand on that? I've never heard that.
Sure. So kind of we can think of what we call the geometry as basically understanding how triangles work. So we know right now if I draw a triangle, all the angles on the inside sum up to, Shirley, sorry, 180 degrees, right? That's considered a flat geometry. Now there's no reason a priori that needs to be the case, actually. You can live, or certainly you can imagine places where different triangles don't sum up to 180 degrees, and those are curved geometries, okay? And what we can do is we can measure triangles really precisely, not just with your protractor, but we can actually measure them across the scale of the universe. And what we find is, as far as we can tell, every single triangle adds up perfectly to 180 degrees. And yet, in order for that to be the case, kind of every single gram of energy needs to perfectly assign. And that seems a little too challenging intellectually, right? And so people posit this question. They're like, is the universe really that flat, or did something else make it that flat? So that is that flatness question. Is this really just down to the proton? You've got all that it takes, or is something else at work? And inflation says you don't need to count protons. It just makes everything flat. Flat till, yeah, really flat.
Okay, question. Question here in the middle, actually. Please go ahead. Go ahead back here while we're.
Well, you said that light is bent by or space is bent by gravity.
Yes.
And it's known to make gravitational lensing. Mm-hmm. How do you know that what you're seeing way out in the distance isn't just some hall of mirrors?
Okay. So again, I think this comes back down to we can calculate what it should look like, right? So that measurement that I showed you actually didn't even, so you look at the star and you wait for the sun to come by, and as the sun gets close, the star seems to move. Okay, so there's no weird set of objects there. The sun comes in and it gets lensed. That's right, so there's more and more deflection, right? So basically, so we can watch the stars move as the sun comes by, and then we extrapolate based on that physics what must happen elsewhere. And so you can calculate and you can say, oh, this object should get distorted in this way. We should see certain phenomena associated with this. And then you can look for it. And indeed, we see that. We see things like multiple images. Okay, so you see different versions of the same galaxy, which is something that happens when it gets lensed. And you can even look at these things called pulsars. So these are things that kind of change in time. And you can watch these images wink a little bit out of phase, corresponding to that time delay. So it is a bit like a hall of mirrors, but it's a hall of mirrors that we expect. I don't know if I answered your question. Kinda, sorta. Grab a beer afterwards. Yeah.
Yeah. So the Big Bang happened 14 billion years ago, and we picture in our head that there is this something in the middle of a sphere where Big Bang happened, and we are somewhere in the surface of the sphere, right? And then when you make your measurements, you measure back to the beginning. However, we can't travel back in history. We can't measure something that happened 14 billion years ago. And I know there is the speed of light, the limitation of the speed of light. So is it more like the reverse situation where we're like somewhere in the middle and we're looking at stuff in the surface?
Yeah, that is the better illustration. So one of the problems with the Big Bang nomenclature is it gives the idea that there's an explosion, that there's some sort of origin, okay? And that's just wrong. What happens is it's just the entire universe, everything, everywhere. As you hit rewind on your DVR, it all just gets hotter. And what happens is as you look out, you kind of take little slices out. So the best way to picture it is actually what you were saying. It's the reverse. Put us in the middle, okay, and you look out. And kind of some of the dots, the raisins that I brought, just said, we're not special. You can go to another galaxy. I'd love the grant to pay me to do that. And you would see the same thing. Okay? Thank you.
Hello.
Hi.
Thanks. Do you or other people that study this have a theory or of what you think you're going to see further?
As we look further back.
Yeah.
Yeah,
Or are
so-
you really just gathering data so that you can come up with a theory that?
So that depends who you talk to. We have people who we call theorists whose jobs are to come up with the theories. And they tell you that they have an explanation for everything you have and are going to see. It doesn't matter what you see. They have the explanation. They published it a long time ago. From the experimentalists, we basically adopt the other perspective, which is you don't have any idea what's going on. So it's a little bit of a mixture of both. We have different ideas. We have lots of ideas. And we entertain some pretty exotic ideas. But for all of them, we ask this question, again, as a hard experimental science, does your idea have does it predict some new measurement, right? And if that measurement, that characteristic, that property is unique to your theory, that's especially profound. So that's kind of the core of the interaction. So theorists try to figure something out, and then we ask, can you predict something? And they say yes, and I ask for money to go and measure it.
Okay. Please.
Are you yourself happy with the term Big Bang?
Not so much. But there's a TV show now named after it, and so.
Okay, we've got one more question, and then I've got a couple for Clarence as well. So please.
Thank you for the presentation, by the way. It was very, very, very enlightening. My question is, can you give an example of practical application of this data?
Practical application of this data. It led to a TV show. Yeah. Not so much. So it gets at the heart of kind of our understanding of energy. Now, are we ever going to make a dark matter generator and extract energy from that? Not while I'm pre-retirement. I'm pretty sure about that. It's more just kind of building up the building blocks of our story. So it appeals to kind of, I think, just questions that we all have and that we all understand. But it won't yield new technology. The detectors might, but the CMB stuff won't.
Okay, very good. A question for me. When did you first decide you wanted to be a cosmologist? What led you to that career choice?
What led me to that? Yeah, so I decided this coming out of graduate school. So I did work actually on dark matter. That's what I did. And we used detectors very similar to the ones under your hand. And I was looking basically for the next thing to do. And the two are bound together, like I said there. The dark matter is part of this larger puzzle that we're trying to solve. So I kind of made a hop and a skip. Decided to come to Chicago to get prepped for the cold before I head to the South Pole.
Okay. Very good. And what does it take to be a cosmologist?
It just takes, I think, a bit of imagination, a bit of hard work, and probably knowing the right people.
Yeah.
Yeah.
Okay. All right. Well, thank you very much, Clarence. Thank you. Thank you.
Thank you.
Good.